is Nicola Sansonetto from University of Verona. So, thanks.
Okay, so first I wish to thank the organizers for this kind invitation and also for organization of all the semester that I have the opportunity to attend at the beginning and also at the end. So thank you very much. And also thank you very much for the opportunity to give this what we call weird talk somehow. It is really tangent, but I hope of interest for some application of things that are studied in this community. The talk is based on a long joint collaboration with Paula. It dates back more than 5 years, the collaboration, and ideas even more. And it will be on Hamiltonisation and integrability of non-Ohmic system with symmetry. So the talk will develop as follows. At the beginning, I will just introduce non-Ohmic systems, some general idea on them, and I will recall which is the link between the existence of first integrals and the presence of symmetries in Hamiltonian mechanics. Then, playing with an example of a toy example of non-Ohmic system, I will derive or introduce the main properties, the main characterization of non-Ohmic system with symmetries. Then I will define properly this kind of system, and I will state the main result, that is exactly to show that this kind of link between symmetries and first integral can be present also in this environment. And then I will deduce two main consequences, that is the Hamiltonization of these kind of systems and also their integrability in the sense that I will be precise later. Yes, non-Ohmic systems. Well, non-Ohmic systems, for me at least, are mechanical systems with constraints in the velocities, constraints that cannot be integrated to constraint on the positions. So their phase space is generally a subset of the tangent or the cotangent bundle, but with some very natural hypothesis, it is a subbundle of the tangent of the cotangent bundle. Their study dates back to to the work of D'Alembert, Euler, and Lagrange, so is quite old. But nevertheless, a complete or say a comprehensive theory of these systems is still not available. Differently for what happened from Hamiltonian systems. So this kind of system has been deeply studied, evolved by Chaplygin and Raut at the beginning of the last centuries, and more recently by many other mathematicians and mathematical physicists. Among them, I would like to mention in really an important alphabetic order Arnold, Deustermatt, Kozlov, Marsden, and Sniatycki. So they come from different fields, and then somehow they course with these strange objects. So I would like to describe some classical example. The first one is called the Chaplygin slate. So it's a platform with a blade, and the platform cannot move orthogonal to the blade. So it's a really toy example of a kind of slate. The second one is the so-called rolling penny. Then here there is a nice object. I forgot it at home, unfortunately, but it's quite common. It's a top that you make it spin. If you make it spin quite faster, then it flips. And the dynamics can be explained in terms of these models. Then, of course, there is kind of solid of revolution that rolls without sliding on a plane. And here there are two nice examples. The first one is a ball, homogeneous ball that rolls without sliding inside a cylinder. And it is claimed to be an example or a model that explains why the balls, I can say, when a golfer putt something, it can happen that the balls go near the hole and then it goes out. So this is an explanation. At the end, I will show you the equation and why it happens, but here there is also an expert on this, if I well remember. And then there is another example that is a ball that rolls without sliding inside a cup. But the cup can also be a cap. The same situation happens, more or less. So what was clear since the beginning is that this kind of systems are not Hamiltonian. So, and already Chaplygin realized this, and he tried to Hamiltonize some simple non-ohmic systems. But what does it mean that they are not Hamiltonian? Well, it doesn't mean, in this, for me, that Noether theorem doesn't hold. So in particular, we don't have a link or a well-known link that from the presence of symmetry and the existence of first integral. So if we have a symmetry which is quite easy to see, then we don't know a mechanism, or it is not clear if there is any mechanism that produces first integrals. And of course, this is a problem if you want to study the dynamics, because first integral helps somehow to study dynamics. So I would like to play a little bit with this non-holonomic oscillator to show what happens in this non-ohmic framework. This is really a toy example that contains many, many interesting things. So it is a free particles with a kind of, let's say, spring-like potential defined on the space that has some property. This S1 times R times S1. This is the configuration space. The Lagrangian is the one of the harmonic oscillator. I'll let mind the Hamiltonian is better for our purposes. And the spring potential is only, let's say, in the y direction, just to have some symmetries. O plus, of course. And now the constraint is described, let's say, like that is Pz is equal y px, and it characterized by non-integral distribution is fiber as given by these two objects. Y, d, z. Okay, yes. Then there is clearly a symmetry of this system. There are translations along the x and z directions. Okay, so there is, let's say, symmetry group whose tangent to the group orbit are given by these two translations. And this symmetry leaves the Hamiltonian invariant, but also the constraint invariant. So the first thing that one would like to see if the associated momenta are conserved. Now, I write the equation of motion. We can write it in many, many ways, but it's just an exercise using Lagrange equation. Yes. So x dot equal px, y dot equal py, zeta dot is exactly the constraint, y px, and then p dot x is equal minus 1 over y squared px py, and p dot y is equal, okay, I wrote here in this way because it's quite general, the situation. Let's call the potential energy like that. So it immediately emerges that the momentum of these two symmetries are not conserved by the dynamics, okay? Nevertheless, one can play a little bit and see that the intersection between these two objects is non-empty, and indeed it is this generated by this guy, and I can take, like I say, just I multiply this vector field by a function. Yes. I call this Z, and then I lift it to the tangent or the cotangent bundle. Okay, so I consider its cotangent lift, and then I impose somehow some kind of momentum equation, and I evaluate everything over the constraint. Okay. And what happens is that we end with an ordinary differential equation for the function f, which is a function of the only invariant variable. So it is a G-invariant function. And the equation is exactly somewhere. It's this one. So this, in one dimension, I can integrate it. I can find f, and in particular, I can write the momentum associated to this vector field z, and it is px 1 py squared. And one can realize that this function is conserved by the dynamics. This is just by playing a little bit with these objects. And then, well, what can I see from here? Well, I have a phase space, let me call D, which has dimension 5. We have two first integrals. One is the one that I just found. The other one is the energy, because it is preserved by the dynamics, so two first integrals. And then I realize that there are something more, because there are so-called free dynamical symmetries. Which means there are free vector fields that commute with each other, and that also they leave invariant the two first integrals. And they are exactly x, the derivation with respect to x, derivation with respect to z, and the dynamics that we call non-holonomic dynamics, this. So we have three vector fields that commute, that are tangent to the level set of the first integrals, the first integral independent. So it is, let's say, quite known that this means that the dynamic is integrable. And since everything is well done in such a way that everything is compact, the dynamics is quasi-periodic on tori of dimension generically 2. So this is something that resembles somehow the structure of integral Hamiltonian systems, in particular of the non-commutative integral Hamiltonian systems. But there is more. One can play a little bit again and say, well, but there is also these two symmetries I can reduce. I can reduce because everything is invariant, so I can define a reduced dynamics. Just put away this equation and this equation. Okay? So the reduced dynamic take place in the reduced space of dimension 3. And in the two integrals descends to the quotients again. So we have two first integrals, and so the reduced dynamic is again integrable. But even more, one can define a Poisson structure in the reduced space. So rank 2 Poisson structure. Indeed, in the tradition of the conference, I cheated a little bit. In this, say, in this space D here, it can be defined almost Poisson bracket. This Poisson bracket is invariant with respect to the symmetry action and descend to the quotient, and it turns out to be Poisson. So it's the rank 2, so it is also something related to the dimension, of course. And it can be written explicitly. So in this case, one can also use Hamiltonian techniques to prove integrability, and the results are exactly the same. So these systems are not Hamiltonian, but they have a flavor of Hamiltonianity somehow after reduction maybe, or because of integrability. And the idea is that to show that this is true in general. In general for this type of system that I will describe today. So this was non-ohmic oscillator. So the idea now is the following. This is exactly what I've sent. And which is the flavor of this Hamiltonian character or hidden Hamiltonian character is that there is somehow a link between the presence of symmetries and the existence of first integrals. And this link gives Hamiltonization integrability. So our aim is to prove that there is this link, and moreover, that if we have a symmetry group, we can exactly say that you have this number of first integrals. And if things are okay with the dimension of the objects, you have Hamiltonization and integrability. Okay, so what is a non-ohmic system? No, for me, non-Ohmic system is just a Lagrangian system with Lagrange of mechanical type. So it is kinetic minus potential energy with kinetic energy of metric type. So it comes from a Riemannian metric. And then we introduce the constraint. We consider the easiest constraint, so described by the constant rank distribution, which is not integrable. So from the physical point of view, it is a constraint linear in the velocities. If we complicate it a little bit, other complicated things happen, and okay, I will avoid this. The equation of motion is, as I told, are just Lagrange equation with multipliers. So standard things in basic physics aspect. But for our purpose, it is interesting to go to the Hamiltonian formulation. So we consider the constraint manifold, which is the image through via Legendre of the distribution D. And then we have these two objects, Hm and omega m, which are the restriction to the constraint manifold of the Hamiltonian and of the symplectic form. And then we define this distribution given by the vector tangent to M that project onto the constraint distribution. So this is a distribution on M. With this object, based on Sniaticchi, we're able to prove that a kind of Hamilton equation holds for the dynamics. So the dynamics is tangent to M, is also a section of this distribution C, and they fulfill this type of equation where everything is evaluated on the section of the distribution. So it's a type of Hamilton equation. They also prove an interesting fact that C is not integrable, and it is integral if and only if the system is holonomic. So this is really a measure of the non-holonomicity of the system. Okay. But these equations are interesting per se, but more than that. It allows us to give a characterization of first integrals in terms of functions and of Hamiltonian-like vector fields. Let's say this way. To every function, we can associate a vector field called the Hamiltonian the non-holonomic vector field of the function, and then a function on the constraint manifold is the first integral of the dynamics if and only if it preserves the constraint Hamiltonian, exactly in the Hamiltonian case. Moreover, here there is at least a link with Poisson geometry. Sure.
The previous slide, but how is it this equation now omega m is perhaps degenerate? So
oh no, okay, I forgot to mention. Omega m restricted to the section of C is non-degenerate. Is non-degenerate. This is the key point. Yeah. Okay. And moreover, omega m induces a bracket of an almost Poisson structure on this constraint manifold. This is a truly almost Poisson, doesn't satisfy Jacobi. But again, we can characterize first integral in terms of the bracket. So a function is the first integral if and only if Poisson commute with the Hamiltonian. Okay. So now it's time to put symmetries and see what happens. So for a symmetry in this case is the easiest one. So we consider a Lie group that acts properly and freely on the manifold and leaves the Lagrangian and the distribution invariant. Then this action induces an action on the constraint manifold that leaves the constraint Hamiltonian and the bracket invariant. So for us, this symmetry is a G action that has these properties. What is even more interesting is that we can consider the reduced space. The dynamics is invariant, so goes to the reduced space, and also the brackets are invariant, so they descend to the reduced space. So also in the reduced space, we have a kind of almost Poisson formulation of the dynamics. Okay, so this aspect of symmetries have been studied since the 50s by the work of this Agostinelli, then rediscovered by Iliev in the 70s, and many other, say, persons then work on this, mainly on reduction or on reconstruction theory. So what was known at that time, at least that more or less 20 years ago, it was clear that the mainly difference between Hamiltonian mechanics and non-ohmic mechanics in relation with symmetries was the following. Not all the components of the momentum map are preserved, and in general it is difficult to say how many and which ones. Moreover, the class of first integrals that a non-ohmic system admits is in general much bigger than the components of the momentum map. And this is what happens in this situation. So one has a symmetry, picks an element of the Lie algebra, and then construct the momentum. Okay? The Hamiltonian is invariant, the original Hamiltonian, and try to write what is called the momentum equation. And what happens is that this is the momentum equation, and in general, this is not zero. It depends. It may be or may not. On the other hand, we can try to mimic what we did here. We consider the intersection between D and this space and play a little bit. So we consider this intersection. Indeed, it is over, but it's essentially the same. Then we consider section of this, let's say, bundle that are combination of elements of the Lie algebra with functions that are depending on the configurations. Then we write the momentum, and now we impose, again, the momentum equation. And it turns out that this object is a first integral if and only if this strange equation is fulfilled. But again, this is not always true. So what is clear is that new concepts were necessary. So let's go for this new concept, that is this definition. So we define a distribution S, which is exactly the intersection between the constraint distribution and the tangent space to the group orbit. Okay? This allows us to introduce this bundle, whose fibers are given by the element of the Lie algebra at point Q, such that the infinitesimal generator lies in this distribution S. Okay? So now this is the strange definition. Consider a function on M. It is called an horizontal gauge momentum if there exists an element of this bundle GS over Q such that the associated momentum is a first integral. And in this case, we call this section an horizontal gauge symmetry. So now the game that we have here is said in more geometric terms. Say, okay, we are looking for sections of this bundle that are horizontal gauge symmetry, or better, we want to select this section in some way. So to do it, we need hypotheses. First hypothesis is the following, is the so-called dimension assumption, and we assume that the tangent bundle is spanned by the distribution times the verticals. Then we can say that a vertical complement W to the constraint is the distribution on Q that fulfills this relation. And it has been proved, I think, by Paula, that this W exists, is free if the action is free, and is this also if the action is free, but with more technicalities. This splitting also induced a splitting of this trivial bundle by the GS that was defined before, and GW, whose fibers are given, again, by the element of the Lie algebra in the point Q, such that the infinitesimal generator is in this space W. Okay, the dimension assumption ensures that this bundle is a subbundle of this trivial bundle. In principle, it is a generalized bundle, so it can be really an ugly behavior. And moreover, it allows us to define this non-ohmic momentum map, which is somehow what we need to define the right objects. It is a bundle map between the constraint manifold and the dual of GS. Okay. Now, look, consider a global basis of the space of section of the distribution GS. The global is bracket because so far it is not important, but it is a key point. This is the first real obstruction to the existence of this gauge momenta that I'm going to find. So let's say that this basis exists. Then every element of the sections can be written in this form as a linear combination of element of the basis times function on the configuration space. So our problem now is to find this function in such a way that this GC is a first integral of the dynamics. Or differently, look for this function f such that Xi is horizontal gauge symmetry. Okay, a step further, we consider another decomposition, now a decomposition of the constraint distribution, split it in a part which is in the vertical and another part which is not in the vertical. This allows us to write the momentum equation that I mentioned before in this term. So where the role of the functions fi is evident. So now we want to find these functions that are the coefficient of the linear combination in such a way that this momentum equation is fulfilled. Okay, now I have to spend some moment to explain what is this object. So, is here? Yes. So, we consider a principal connection of the trivial bundle Q times G over Q, and this decomposition inducing the decomposition of the connection. Now, this allows us to write this object, sigma, in this way, that arises from writing explicitly the momentum equation. And I want to just to say something about these two terms. This term has been introduced, if I well remember, by Jair, yes, right? And then has been proved that this term, which is the pairing between the standard momentum map with this G-value to form that describe the curvature of the vertical complement, is independent from the choice of the basis, while the other term does depend on the choice of the basis. Nevertheless, this sigma is G invariant, and we will use it. Okay, this sigma also arises from this observation. We want to write the momenta, and then the relation between the momenta and the differential over the space of sections are exactly given by sigma and the restriction of these two forms. Okay, so as I mentioned, this sigma is G invariant. And now, what to say about this momentum equation? At first, this momentum equation is a partial differential equation, quadratic in the velocities. So it has a nice property, but it's a PDE. So in particular, it doesn't say anything about the global aspect of the first integrals. Maybe they can exist, but locally, and we know that locally they always exist. But we want to have some global information. So what to do? When we use this decomposition, of course, we need to restrict the kind of system that we consider, but nevertheless, we will see that there are many. So we assume that this space H is one-dimensional. That means that the shape space, Q mod the group, is one-dimensional. If this is true, we can write the section of the bundle GS as linear combination of the basis with functions that are functions on the shape space. So there are G-invariant functions. And this, since this space is one-dimensional, tell us that the momentum equation now is a system of ordinary differential equation. And in this case, we can have more information. In particular, we can state our main result. Main result is the following. We consider non-ohmic system with a G symmetry, and we assume the following. The first, it was the dimension assumption that gives many information. Then we assume that this bundle admits a G-invariant global basis. The G-invariant is not an hypothesis in Beans. It is a property that he has. Then we assume that the distribution H is one-dimensional, or if you prefer, that the shape space is one-dimensional. And finally, we have this ugly condition, ugly technical condition, that comes from a proper choice of the coordinate in a momentum equation. And if these four conditions hold, then J is a first integral of the dynamics if and only if the functions that are used to define the infinitesimal generator are solution of the momentum equation. This is the momentum equation here written in coordinates. Okay? So, and these objects are function on the shape space. So what happens is that if these four conditions hold, we have K, which is equal to the rank of GS, or if you prefer the rank of S, functionally independent horizontal gauge momenta associated to the system. So we have been able to produce a precise number of first integral, which is the intersection of the distribution with the tangent space to the group orbits of first integrals out of a symmetry. So if you may ask me, it is the Netter theorem? No, it is not. But it is a way to construct this link out of a symmetry. And what is even more interesting is that these first integrals are automatically functionally independent, and moreover, they are G-invariant, so they descend to the quotient. Okay, one may also ask, okay, you have so many hypotheses that apart from this toy example, it is impossible to have them. Well, it is not true, and here there is a list of examples. I want to mention them. Okay, this is my toy example because all the computations are explicit. Okay. Then the vertical coin is really a coin, but that also has a constraint to stay vertical. So it is not really feasible, but it works a little bit. It is also a nice example. For example, now we know that there are two first integral of gauge type, and one of the two was not known, was recently discovered. Then the type top has this property as well. This is the symmetry group. Dimension of the space is 2, and indeed it fulfills all the properties, and we can find two first integrals. I want to mention that for the type top, for the falling disk, for the body of revolution, and for the ball in a cup with a generic profile, we know that these two first integrals exist, but in general, we don't have their explicit form. They are given as solution of the momentum equation. The momentum equation has this solution, but we don't know an explicit formula. Right. Okay. Now there is this toy example is quite famous. It is the snakeboard. It is a kind of skateboard, but with the wheel that can move. Okay. It is well studied since it was one of the main, toy that came from this geometric control theory approach. Well, it was not known that he had these two first integrals, and it was not known that somehow it is integrable in the reduced systems and also in the unreduced one that I will show. Okay, so, and the list can continue a little bit. Okay, so the hypotheses are strong, but there are systems that have these properties. And on the other hand, if you look for finite dimensional Hamiltonian interval system, there are not many. Then one starts with them, and with some perturbation, maybe you want to study something more. But the number of interval systems is usually small. Okay. So I don't expect to have much more than this. Okay, what about Hamiltonization? So here there was this Poisson structure, and here, in a more general setting, well, we know that we have this almost Poisson formulation in the full space, and that we can reduce, and we have an almost Poisson formulation also in the reduced space. Okay, but now we want to play a little bit with sigma, with these two forms that I mentioned. And we use it to consider a gauge transformation of this Poisson bracket, almost Poisson bracket. And we define here another bracket with M. This bracket, since sigma is G invariant, descend to the quotient. And so we have another structure here, M, on the reduced space. And what it turns out is that under the hypothesis of the theorem, these reduced brackets are indeed Poisson. The leaves are given by the horizontal gauge moment. No, sorry. The leaves are given by the momenta of the chosen basis in general. But the problem with this Poisson bracket is that it's not dynamical. It means that the dynamics is not Hamiltonian with respect to this Poisson bracket. But we can have, let's say, a clever choice of the basis. So we can choose the basis of our space of section to be what are called here horizontal gauge symmetries. If we choose the basis to be horizontal gauge symmetries, then the dynamics is tangent to the leaves in this case, because the leaves are given by the level set of the horizontal gauge momenta. And then the bracket are Poisson, but are also dynamical, meaning that the reduced system is Hamiltonian. And this happened for all these cases. So in all these cases, in the reduced system, we have a reduced rank 2 Poisson structure. And now I want to introduce a little bit about integrability. And before doing it, I need to recall a notion of integrability outside the Hamiltonian setup. So this notion is mainly due to Bogoyavlensky, but at the same time has been formulated by Fedorov in a paper of 2 pages in Russian, so it's been somehow forgotten for a long time. And then has been also reformulated by Zung, that he called it QP integrability. So the idea is the following, it's very general. So indeed, I prefer to define it not a theorem, but a characterization of integrability. So we consider a d-dimensional manifold, and then we consider a submersion on this manifold on d minus k, for some k less than d. We assume that the level set are compact and connected. Then we also assume that there are k everywhere linearly independent vector fields, which pairwise commute, and that are tangent to the level set of the submersion. If this is the case, then the fibers of the submersion are k-dimensional tori. And if we can say that a vector field x on M has this function as first integrals, and this y1, yk as dynamical symmetries, then its flow is conjugated to a linear flow on the fibers on the tori. So it's something that is really close to Liouville-Lanourt theorem, or to be more precise, to what he calls Michenkov-Fomenko theorem. So indeed, also the geometry of this kind of system is really close to the one of non-commutative integral systems. And of course, yes, what is here is something that is for me to remember, their properties, nothing important. And what about our systems? So I can restate this integrability in the case of reduced spaces. In this way, I have an Ohmic system. It fulfills the hypothesis of the main theorem. Then we assume also the A rank of H is 1. We call K the rank of S. Then we know that the reduced space has dimension K plus 2. Moreover, we know that there exists k independent G-invariant horizontal gauge momenta that descend to the quotient. Then there is the energy, because all this system that has linear constraint in the velocity has preserved energy. So we have an energy momentum mapping that gives the orbit of the reduced dynamics. So you can integrate by quadrature the reduced dynamics. But if you have if this map, if the energy momentum map is proper, then indeed the reduced dynamic is periodic, and it defines an S1 principal bundle. Using technique from reconstruction theory, one indeed can prove that if the symmetry group is compact, then the complete dynamic is generically quasi-periodic on tori of dimension h plus 1, where h is the rank of the group. So in this setting, in the reconstruction setting, the maximal tori is the object that plays the central role. If G is not compact, it is not easy to prove, but a similar result happens, and it depends on the flavor of some, let's call it them, subvariety of the Lie algebra. But here is something that goes a little bit beyond my knowledge, but there are results also in these directions. So what happens is that our theorem also guarantees some kind of integrability of these systems. Integrability that really resemble the Hamiltonian one. I forgot to mention that we can also have another kind of integrability because we can use Hamiltonization. Because the reduced space is Hamiltonian with respect to a rank 2 Poisson structure, and we can use energy to integrate the reduced dynamic leftwise. And the good thing is obviously that the two approaches coincide. Okay, so yes, we have again this table. So when you see a compact Lie group, then the system is periodic. The reduced system is periodic, while the complete system is integrable in tori of some dimension. When I mean generically, it means of dimension up to is that there can be resonances in the reconstruction procedure, okay? Because we use the circles, and the circle can have the same frequencies. So in particular, I would like to mention the cylinder in these last 2 minutes. So cylinder is here? Yes. Okay. Okay. The cylinder has configuration space R2. No, sorry, it's S1 times R times SO3. Okay. The distribution has dimension free, rank free. Okay. I don't want to write it explicitly, but the constraint is non-rolling constraint. So it involves 2 conditions. The tangent space has dimension 5, so we goes to dimension 3. So our phase space has dimension 8. Then when you write the Lagrangian, you immediately see that the attitude of the ball doesn't play any role, and also doesn't play any role in the constraint. So the equation of motion are freely given in the reduced space that I call M5, which is M mod SO3. Okay. For free, the equation of motion are defined in this space. But then we can use also the other symmetry given by S1, and we end up with 4-dimensional reduced space. In this 4-dimensional reduced space that I call M4, we can find 2 horizontal gauge momenta. One is a relation between the angular velocity with respect to the vertical and the angular velocity given by the S1 action. And the other one relates the height of the ball with the angular velocity with respect to the normal. So, and then there is the energy. Then we have 3 first integrals. and one symmetry, which is the dynamics. And then I can show you the curves that describe the dynamics. This is the oscillation of the Z. So it means that the center of mass of the ball do this. And this is one of the reasons that it can escape when a golfer putt, the ball can escape from the hole. On the other point of view, you can see here the dynamics on this space. And dynamics on this space is periodic with two motions. There are techniques to see that it is true. So it's a really interesting example. Also, this one is completely explicit. The same situation for the ball in the cup, but there nothing is explicit. So I want to conclude with some, let's say, perspective. So I'm so happy that this long project see a kind of light at the end, but many other questions remain open. In particular, I want to mention 3 of them. Oh, the first one is, where is it? I forgot it. Okay, the first one is that I would like to extend somehow this theory to group actions that are not on the configuration space, but they are naturally on the phase space. Because in many non-Ohmic systems, there emerges, let's say, first integrals that are not linear in the velocity, but are quadratic of polynomial in the velocity, or even that are transcendental functions. The other thing that is of interest is what happened to the global aspects of the vibration in tori given by this Bogia-Wolensky approach to integrability. And the final one is something that I think is really complicated, and it is what about Hamiltonisation, not for rank 2 Poisson structure, but with something bigger. Because also at this level we have integrability, two-dimensional tori, for example. We know that in a neighborhood of each tori there is a Poisson structure. It's easy to write it, but can be somehow extended. There are some examples of it, but they contain many singularities. So it is, of course, these systems are not Hamiltonian. We know it, but Hamiltonian structure in this framework plays the role that they help us in understanding the dynamics. Thank you very much for your attention.